Yeah, welcome to these slides on interpolation, approximation, and extrapolation, part of the computational methods course. And let's crack straight on. And this is just a slide to describe the learning objectives for the whole set, and also in the next lecture as well. And the main learning objectives are really to sort of get a sense of the difference between the way sometimes data are collected in a discrete setting, and the fact that sometimes we need a continuous representation of that data. We want to be able to evaluate an estimate for some measurement at arbitrary locations and not just at the discrete locations where we sample the function. And there are sort of three main methods that we can use to sort of help us get that continuous representation, and that is interpolation, approximation, and extrapolation. And to become familiar with some of the sort of popular techniques of carrying out interpolation. So this is just basically an outline of the methods that are in the slides. There are sort of broad distinctions between either using a single full polynomial to interpolate all of our data, or to do something called piecewise interpolation, where we only interpolate small sections of our data and join up the pieces. And this can be done either in a linear way or using nearest neighbour interpolation. And then towards the end of the lecture, we'll look at smooth interpolation, where we use some cubic polynomials to get a smooth representation of our interpolation function. So the motivation or examples are, that we typically make measurements at sets of intervals. So we might take the pulse of a patient once every 24 hours, or we might look at the share price of a company every Friday morning or something like that. We might take the temperature at intervals in space this time along a railway every 1 kilometre. Or we might measure the altitude of the ground over a square grid of landmarks. That's an example in 2D. Or if we're taking an MRI image, we might tune the MRI scanner to measure tissue water content over a 3D grid, and to provide us with a 3D image of, say, somebody's heart or brain. Or we might measure the position of a moving particle every 1 second or so. The thing about these data is that necessarily they are all discrete measurements. They happen at fixed intervals in time. And we can illustrate that here. And because we have a graph to show along the horizontal axis the points at which we make measurements. These can be spatial locations or they can be time points, and they're indicated by the little sort of grid marks along the horizontal axis there. And so they're all discrete, they're all separated from each other. And we can make measurements at these discrete points, and those measurements are all indicated by the height of the red dots there. And for the time being, we'll assume that these sort of locations where we're making the measurements, or these time points, they're regularly spaced, either in space or in time. And the locations are sometimes called knot points, so I might use the word knot points to describe these points at which we're doing the sampling.
So we make these measurements at a set of discrete locations. We're going to call these sort of X locations in this case. Here we've taken N measurements, and the actual values of our measurements, indicated by the height of the red dots here, we'll call those the Y's, from Y1 up to Yn, one for each measurement. And so a natural question then is that if there's some other location that's not at one of the points that we made a measurement at, some new location, which we call a general X in this case, we want to ask the question, what is the value of Y that corresponds to that? Because typically we won't be able to measure at all locations. And just as an aside, the locations where we do make the measurements, these X locations, X1 up to Xn, we often call those knot points. So if we want to find out the new value at a new location, we can use this process called interpolation. And that means that we need some kind of function that we can use to estimate the measurements at the new knot point. So there's more than one possible function that we can use, and we can fit lots of different functions to these data. So here's one possible interpolation function, right? It starts with our discrete data, our red blobs, and it gives us a continuous function, which is here shown as a black line. And this is an example that shows linear interpolation. Every point is joined with a straight line to the next point. Every measured value at each knot point is joined to a measured value at the next knot point. And one bit of terminology to go with this then is that there is a support region, and our interpolation function isn't defined everywhere, but it's only defined on a support region. And this support region is generally within the range of the original x values. And that's what interpolation is about. Here's another example of an interpolation scheme for the same data this time. But instead of using a linear interpolator, we've used something called a spline interpolator. This is just to give you an illustration of what we can do. Same data, different interpolation scheme. And here's yet another interpolation scheme, again for the same data. This is an example that shows nearest neighbour interpolation. It gives us almost a continuous function. It's continuous and horizontal for most of the time, but when it reaches a kind of halfway point between two measurements at two adjacent knot points, it has a discontinuous jump, which is shown here by the dashed lines. And we can see that our x value, here in this case, will be assigned a value that is the same as the value that its nearest knot point measurement would have got, which is sort of shown somewhere around here at the bottom. So this is an example that's slightly different. This time, the same data again, but what we're not doing is interpolating. What we're doing instead is approximating. We're approximating our data with a spline, so we call it spline approximation. And this is partly to reflect the fact that we accept that there might be errors in our original measurements. We don't actually have to interpolate every single point. We can sort of go near them, and as long as we get the rough shape of the data right, then we can say we're approximating our data. And then for this approximating function, at this location x, we can say this is what we estimate our value should be. So interpolating our data means that we actually have to go through our data. And in contrast to what we've talked about so far, interpolation of the data, or going through every measurement exactly, and approximation of the data, which is sort of going near them, there's a third term that we need to understand, which is called extrapolation. And this allows us to estimate the measured value at new locations, but in this case, our new locations can actually be outside the range of our original measurements, beyond the original support of the original measurements. And extra means outside in Latin, so hence the term extrapolation. So this is just to illustrate that. So we have our original data. We have some function which is actually inside the range of the data is approximating it, but we extend this function outside the range with these dashed lines shown here, and it means we can estimate the new values for the function at new data locations beyond the original support, and hence carry out extrapolation. And this is just to illustrate that we can do interpolation in more than one dimension. So we have an example shown here. The picture on the left illustrates for us a two-dimensional function. So this is a 2D function because at each point in this 2D plane we have a functional measurement, which is the intensity of the image. Very high values would tend to be white, and very low values would tend to be dark or black. And we can imagine that we can take a sample of measurements from this 2D function. So instead of sampling it continuously in space, we take a regular grid and we take a measurement at each location. And so we end up with this sort of dotty little diagram on the right hand side. And let's imagine that we didn't have the original 2D function, but we only had the sample measurements. Then we would like to reconstruct what the original 2D function was. And we can do this again in more than one way. So if we use nearest neighbour interpolation, then from our sampled measurements shown on the right here, we obtain this sort of blocky image here, and again a 2D representation. And this slide here shows that we can use linear interpolation in 2 dimensions as well, as we did before. And again, starting from these sampled measurements on the right hand side, we can reconstruct this linearly interpolated estimate for our original function. It's not the same as our original function. We haven't recovered the whole exact thing. We've got a blurry version of it. But it's just to illustrate the point that we can do interpolation in 2 dimensions. And this is another interpolation scheme in 2D. This time it's using cubic interpolation. Again, just illustrations and examples. So let's talk about some methods then. Here's a very simple example. Let's have 2 knot point locations, x's, x1 and x2, and 2 measurements, y1 and y2. And it's very simple to interpolate 2 data points because we can just fit a straight line between the two. And if we have 2 points written with coordinates forms here, x1, y1 and x2, y2, then we can use our favorite style to write down what the equation should be. So the general equation, the general form for y and x, is written in terms of the measured values at y1 and x1 and y2 and x2. And we can rearrange this to in the form that we like. So like we might rearrange this to the form y equals mx plus c, and we can evaluate the equation for any x between x1 and x2, and that would be a direct interpolation. And that's just illustrated here, joined by a straight line. It's the simplest example, this is, of full polynomial interpolation. We have 2 points, we have a straight line or a linear equation between them, and a straight line equation is basically a polynomial of degree 1. And if we had more points, then actually we can fit polynomials with a higher degree. And the next few slides will illustrate this. So here's an example. Now we have 3 points. And this gives us a quadratic equation, which is a polynomial of degree 2. And the form of this equation is shown here. It's going to be a function that provides us with a y value when we're given an x value, and it has 3 coefficients. In this case, we've just written them down as a, b, and c. And if we evaluate for a given x value and a given set of coefficients a, b, and c, we can calculate what y is. So in this case, we have some measurements, we have some locations, x1, y1, and x2, y2, and x3, y3. And if we want to find out what is the correct quadratic, which quadratic will fit through these points, we can set up 3 equations in the 3 unknown parameters, and we can solve for a, b, and c. And we can write that down here. We've written down 3 equations at the bottom. The first point provides us with the first equation, the second point provides us with the second equation, and the third point provides us with the third equation. So we have 3 equations. Our unknowns are a, b, and c. We know what the x's are, we know what the y's are, so we can solve for a, b, and c here, because it's a simple system of equations. So with 3 points, we can have a quadratic equation fitted to them, and that would be a polynomial of degree 2. We can carry on like this. So if we have 4 points, we can have a cubic equation, or a polynomial of degree 3. And in general, if we have n points, we can always fit a degree of polynomial that is 1 less than the number of points, n minus 1. And that's shown here as a longer formula, as f of x equals coefficient times power of x plus next coefficient times next power of x, all the way down to the lowest powers of x. So the last one is a1 times x, and then the last coefficient is a0 here. And we can write that a bit more simply if we use the sum notation. So we're doing a summation from over an index k here, from 0 up to n minus 1, of each coefficient ak, in this case, multiplied by the power of x, x to the power k. So we can actually have a formula in general for n points. So if we're given n measurements, x1, y1, x2, y2, up to xn, yn, we can find a polynomial that will fit through all of these data by using a formula due to Lagrange. And this is the Lagrange form written out here. It's written as a sum of products. So we're going to go into a little bit of detail on this. So we'll try and sort of pull apart the different components of this formula. So you can see the summation over here on the left-hand side, and it's a sum over everything inside these sort of curly brackets times a measurement value yk. So inside the big brackets is a product, right? This pi notation is a product of a series of fractions. X is their free variable, and the xj's and xk's inside are the measurement locations, or the knot points that we had. And each of these products is over all values of j that don't equal k. K belongs to the summation on the outside. And each of these polynomials therefore has almost n terms, but because we're not including k, it's n minus 1. So let's just break this up. Let's just remind ourselves that in green here are the given values that we've been provided by our measurements, and x is our free variable, and when we put in a particular value of our free variable, we can calculate the polynomial. So here's an example now for 3 points, just to make things a little bit simpler. This is the Lagrange form for 3 points. So let's say we have 3 knot point locations, x's, x1, x2, x3, and for the sake of simplicity, let's just say that the values are 1, 2, and 3 for them. And let's say we take 3 measurements, 2, 1, and 4. So you can see I've done this to scale here. There's 1, there's 2, there's 3 on the x-axis, and there's 1, 2, 3, 4 reading up the y-axis here. So this formula then can be broken down to a much more simple form for these sort of 3 points here. So we have 3 terms that are being added together basically. Each one of them is a polynomial in x. Each one of them is actually a degree 2 polynomial in x. So let's pick our first x value, which is x equals 1, y is equal to 2. So we go over all products of x minus 2, x minus 3 in this one. So we've missed out the x equals 1 here, and we've missed out the x equals 2 here, and we've missed out the x equals 3 here. And these are also differences for the first one. There's k equals 1, there's k equals 2, there's k equals 3, and we can follow a pattern here to find out what the polynomial should be. These are the measured values. There's the 2 corresponding to there, there's the 1 corresponding to there, and there's the 4 corresponding to there. And so we end up with 3 different terms added together. There are some problems with full polynomial interpolation though. It can actually go bad, and we can have let's say for example a function here. It's a real function, 1 over 1 plus x squared. It's shown in red in dashed form. It's a continuous function. It rises to about half at x equals 0. No, it doesn't. It's 1 at x equals 0. And we can take measurements of these points at integer locations here from 0, 1, 2, 3, and so on. Let's say we take 5 on the negative side and 5 on the positive side, and our x equals 0 as well. Let's say we have all of those 11 sample points for this function. If we use these sample points and pass them into the Lagrange form, then we end up with something that looks very different from our original function. We end up with, in this case, because we have 11 points, we have a degree 10 polynomial. And the problem with it is it ends up being very oscillatory, or it moves up and down quite a lot. And it's hard to control it away from the measured points. So there is a downside to actually trying to fit a full polynomial to all of our data. So an alternative to fitting a full polynomial to all our data is called piecewise interpolation, where we do interpolation piece by piece on our discrete data. We don't try and fit a single function for everything, but we fit separate functions, and we do this for intervals that are defined by our data. So if our x locations for our data are x1, x2 up to xn, then each pair of successive knot points gives us an interval. And for each pair of successive knot points, we assign a function. So in this case, for our first interval, we can put our f1, and for our second interval, we can put f2 in, and so on. This is not a very good interpolating function, but it's just to illustrate the point that we can have different functions, one for each interval.
So a good example of piecewise interpolation is piecewise linear interpolation. So again, we have a set of measurements, which are shown here by a set of y's at a set of knot point locations, which are shown here by the x's. We have n values in this case. And then if we have a new x value that we'd like to find out an estimate for, we look for a specific interval. In other words, we look for a value of k such that our x value is between xk and xk plus 1. So we're just looking for the two successive knot points that are on either side of our x location. And then the linearly interpolated estimate for y is just the straight line function joining xk and xk plus 1. So if we look at the bottom equation here, this is just the equation of a straight line between xk and xk plus 1. And so it can be written as sort of the difference between the y's multiplied by a fraction, and the fraction here is the amount we've gone from xk to the next knot point once we've reached x, and that's added onto the value at yk. That's one way of writing it. There are other ways of writing it, as we'll see. And the function itself looks like a set of straight lines, each one joining one knot point to the next. But we can rewrite this estimate for y. We can write it in a slightly different way. We can write it as a blend of the two measurements at the ends of the interval. So we have yk here and we have yk plus 1. And if you do this sort of algebraic manipulation, you can show that this blend can be written in this form. So it's a fraction here times yk plus another fraction times yk plus 1. And this fraction here, the u, is just simply a fraction of how far we've gone from xk to the end of the interval, xk plus 1, when we've reached the point x. So just simply this fraction here, u, this proportion of how far we've travelled, can be used to define a blend that combines yk and yk plus 1 to give us our estimated value, our interpolated value y. This blend relies on this fraction, and this fraction, we'll call this a change of variable, because it gives us, from x, it gives us a new value u, and it can do this for any interval at all. And this variable u is a local variable over each interval. So just to illustrate that a bit more, here's our blending function. I've switched suffixes here to y, but that doesn't really matter. So we have an interval between yi and yi plus 1. We blend them together with u and 1 minus u. And if you note that the weights add up to 1, so we've got a linear combination of the two. And here's our expression for our change of variable, u in terms of x. So if we look at what happens when the value of x varies from the start of the interval at xi up to the end of the interval at xi plus 1. If we do that, then u will vary from 0 to 1, and that's sort of illustrated here. So if if x is a quarter of the way along, then u is going to be 0.25. If x is half the way along, then u is going to be a half, and so on. So the intermediate values give us our intermediate points. It's the local variable u that tells us how far along the interval we are, and expresses that as a number from 0 to 1. So to summarize then, we get a set of functions with piecewise linear interpolation, one for each interval, and our intervals are all listed along the sort of left-hand side here for our numbers from x1 to xn. And our functions now, we can view those as functions of u rather than functions of x. They're all functions of this local variable, and this local variable u depends on the x's at either end of the interval. And u varies from 0 to 1 across each interval. And so that makes all of our functions kind of similar in a way. And some notes about piecewise interpolation is that mainly it does provide us with a continuous function. The whole function is completely joined up, there are no gaps in it, but actually it's not differentiable at the sample locations. So we can see that there are little sharp corners at the sample locations. So in general, what we have is a continuous function, but it's not continuously differentiable. It's not a differentiable function. It's got some jags to it. So here's another example, a separate example of piecewise interpolation. This one is called nearest neighbour interpolation. And this one is a bit simpler than linear interpolation. So again, we have our measurements here, our y's, and our knot points here, our locations x. And if we get a new x value, we just look for the individual knot point location, the individual value of I, such that x is closer to I than it is to any other knot point. So we just find the nearest neighbour for x. And then the interpolated value for our x value is just going to be the value at the nearest neighbour. So in other words, we just take the y value of the nearest measurement location. So in terms of a local variable u, we can imagine there's a little interval here somewhere in our data between xk and xk plus 1. Then as we move gradually and continuously from xk up to xk plus 1, then before we've reached the halfway point, so in other words before u is equal to 0.5, then the values that were assigned are all the same value as our previous knot points values, in other words yk. And as soon as we reach the halfway point, there's a jump, and we start to assign the value at the next knot point, which is yk plus 1. So that's why we get these horizontal bars stretching halfway away from each knot point to the next, and then there's a discontinuous jump there. So as I've just said, we don't even get a continuous function when we do nearest neighbour interpolation. It's almost continuous, it's just not quite continuous, because there are these jumps at the halfway points between knots, which we see here with the dashed lines. But it's very easy to implement, and it's very fast. So just to summarise, a little mini summary, we have nearest neighbour interpolation and piecewise interpolation. Nearest neighbour is almost continuous. Piecewise linear interpolation isn't actually a continuous function, even if it's not differentiable. Piecewise linear interpolation is fairly easy to calculate, but nearest neighbour interpolation is super easy to calculate. And here are just some different terms that also are used to describe nearest neighbour interpolation. So we've looked at nearest neighbour interpolation and linear interpolation. So the next question we can ask is whether there are some other options that are a bit smoother but still piecewise. In other words, can we get a sort of set of smooth curves that we can fit piece by piece along the intervals of our data? Now the slight difficulty here is that there are lots and lots of different types of curves that can be made to fit our data, and that's just illustrated on this slide here. And we need to find a way of choosing between them, in other words trying to decide what are good curves and what are not such good curves. So when we want to do smooth piecewise interpolation, there are actually two kinds of data that we're trying to interpolate. We're not just trying to interpolate the measured y values as we were before. These are the sort of heights of the red points at each of the knot point locations, but also we're trying to measure we're trying to interpolate rather the gradients or the first derivatives of our functions. And here we've got two illustrations for the same data set. So in terms of the same measured y values, so if you look at the heights of the red points, it's the same in both cases on the left and the right. But the little lines illustrate for us the derivatives of the function that we'd like to go through the function. So it's the same data set, but the derivatives are slightly different between the two. So we're trying to imagine a trace of a line that passes through both of these. So like I say, we need to measure y values, but we also need to measure derivatives as well, or assign derivatives, and we'd like our function to go through them. So we need to specify derivatives, and hopefully our derivatives shouldn't be too wild in between. So to illustrate that point, for the same set of derivatives, if I toggle between the two, these are our derivatives, and these are the functions that go through. So same measured y values, but different derivatives, so we end up with two different smooth curves that go through them. So we need to specify our first derivative at each of our measured locations, at each of our nut points. And these should be sensible, they should be supported by our data, and they can also, if we like, take into account the measurements around the neighbourhood of each location. So they should sort of relate to the measurements at the neighbourhood so that the interpolation function doesn't measure too wildly. And if we look on the sort of left-hand side here, you can probably see that this choice for the derivatives of a interpolating function are probably a bit more sensible than this choice of the derivatives for the function. So we're still working piecewise, we're still working with intervals in our data. So every function is defined on an interval between xk and xk plus 1. And we want to interpolate the measured values. So in other words, we want to interpolate the y's, yk and yk plus 1. And we also would like our function to satisfy these first derivatives, which are illustrated by these green direction lines here. So this is the gradient gk at the first knot point in our interval, and this is the direction of the gradient at the end of our interval. And we'd like our smooth curve, which is here shown by the dashed line, to satisfy all of these constraints. And because we've got two constraints for the gradient and two constraints for the measured values, we end up having 4 constraints for each interval.